How do you measure something you can't even see? Today, we're going to dive into the hidden world of materials to uncover a secret magnetic personality that every single thing has. And we'll see the incredibly clever way scientists finally figured out how to make it visible.
Okay, so let's start with something we all think we know. You take a magnet, you bring in your something metal, and it sticks. Simple, right? But what if I told you that sometimes a magnet does the exact opposite? That for some materials, it'll actually push them away. Yeah, it's a real thing, and it's the key to our whole story today. This strange push and pull behavior is happening all around us, all the time, completely invisibly. To really get what's going on, we need to take a closer look at how different materials actually respond when a magnetic field shows up.
And it really just boils down to two opposite reactions. On one side, you have materials that get pulled toward the strongest part of a magnetic field. This weak attraction is called paramagnetism. But on the other side, you have materials that are actively pushed away from that strong field. And that weak repulsion, that's called diamagnetism. Two totally different behaviors from one invisible force.
So what's the deal? What decides if a material is going to be a puller or a pusher? Well, it turns out that every substance has its own unique magnetic ID, a kind of hidden code that defines its personality.
And this is it. This is the secret ingredient. It's called magnetic susceptibility, and it's represented by that Greek letter chi. Just think of it as a rating for how much a material is going to react to a magnetic field. And believe it or not, this one single value is what dictates everything, whether it gets pulled in or pushed away.
This table just lays it all out perfectly. You've basically got three magnetic personalities. If that susceptibility number, chi, is small and negative, boom, it's diamagnetic and it gets repelled. If it's small and positive, it's paramagnetic, weakly attracted. And if that number is large and positive, well, that's ferromagnetism. That's the super strong attraction you're used to with things like iron. It all comes down to that one value. Okay, so we know this property exists, but how on earth do you measure a force that's so incredibly weak? I mean, you can't just stick a magnet to it and see what happens. You need a trick. And that trick involves breaking the rules and creating a little chaos.
And here is the absolute key, right from the source. If you put a material in a perfectly uniform magnetic field, one that's the exact same strength everywhere, guess what happens? Nothing. Absolutely nothing. There's no push, there's no pull, it's a total magnetic standoff.
So, to break that stalemate and actually generate a force you can measure, you have to use a non-uniform field. That just means the field has to be stronger in one spot and weaker in another. That difference in strength is what finally gives the material a nudge, telling it to either move toward the strong part or run away from it. Now, armed with this clever insight, scientists designed an experiment that is just brilliant. They use this non-uniform field idea to do something that sounds pretty much impossible, to literally weigh an invisible magnetic force on a scale.
This whole setup is called the Gouy Method. And I know, it might look a little complicated, but the idea behind it is pure genius. You've got your sample, a big electromagnet to create that special uneven field, and a super sensitive scale. The whole point of this contraption is to turn that tiny magnetic push or pull into a number we can actually read.
And here's the play-by-play. It's actually pretty simple. First, you hang your sample from the scale. Second, you position it just right so one end is deep in the strong part of the field, while the other end is way out where the field is basically zero. Then, step 3, you just turn on the magnet and watch the scale. That magnetic force will either pull the sample down, making it seem heavier, or push it up, making it seem lighter. That's it.
And this is what it looks like in the real world, not just a drawing. You can see the electromagnet, the power supply, and right there in the middle, the digital scale with the sample hanging down into the field. It's so cool to see the theory become a real working machine.
So the scale gives us a number, a tiny change in weight. But we're not done yet. That's just our first clue. Now comes the fun part. We get to decode that number to find the real prize, that magnetic susceptibility we've been hunting for.
And the secret to cracking the code is this beautifully simple relationship. It turns out that tiny change in mass, the scale measures, is directly proportional to the material's magnetic susceptibility. They're locked together. If you can measure one, you can figure out the other.
This connection is all wrapped up in this neat little formula. Now don't let the symbol scare you. It's way simpler than it looks. All it's saying is that the change in mass, that's delta M, is proportional to the susceptibility, chi, times the magnetic field strength squared. This is our recipe for getting the answer. Now, to get a really accurate answer, we don't just take one measurement. We do it several times at different magnetic field strengths. Then we plot all that data on a graph. the change in mass versus the field squared. And when we do that, something amazing happens.
We get a straight line, and the slope of that line, how steep it is, isn't just some random number. That slope is the magnetic susceptibility. We've done it! We've used a scale and a magnet to measure the invisible magnetic personality of a material. A total aha moment. So, we went on this whole journey just to find one number. You might be wondering, so what? Why does measuring this invisible property actually matter so much?
Well, it's a huge deal. First, it's a fundamental way to classify and understand what things are made of. But even more than that, it gives scientists deep insights into a material's atomic and molecular structure. If you're designing new materials for, say, data storage or creating special polymers for medical devices, knowing this value is absolutely non-negotiable. And finally, it's just a fantastic story of scientific cleverness, proof that with a smart setup, we can find ways to measure the invisible forces that shape our world. Which leaves us with a final thought to chew on. We found a way to see one hidden property of matter. What other invisible forces are out there, quietly influencing everything around us? And what brilliant new experiments will the next generation invent to finally bring them into the light?